Alright guys, welcome back to Circuits. Yeah, if you just walked in, homework's here to turn in. These are homeworks and quizzes to pick up. Preferably pick them up later now that we are starting class. I guess I have a few announcements to make before we get going with anything circuits related. First of all, if you look at the course webpage, we now have a grader, so I'm not going to be grading the homeworks anymore. I'll be grading the quizzes, but I won't be grading the homeworks. His name's Abraham. He works in my group. He has the same office area as me, not the same office, but he'll have office hours. His email's linked here also if you need to email him for any questions about grading. He's going to grade similarly to how I do. It's just going to lighten the load for me as far as grading homeworks, because it does take some time. He'll start grading the homeworks on Monday. I'm still going to grade the homeworks you guys turned in today. But from now on, for those of you here that may not make it to a lecture and you need to submit it via email, do not submit it to me. Please submit it to him because I'm not going to be grading them anymore. And if you email it to me, you're just going to create more work for me. So please email it to Abraham. If you're turning it in class, obviously, you're still going to bring it to class and I'll give it to him. Okay, so that covers the grader. I'm going to be grading your quizzes and your exams. He's just going to be grading your homework. So, but also, if he has office hours that you can make it to and you can't make mine for some reason, you're welcome to go to his office hours and ask questions. He's well-versed in circuits, so he'll be able to help you out too. So the quiz last time didn't go great. Some people got it right, a lot of people got it wrong, partially, and so I made a little quiz 3 solution video. It's linked here to last lecture, so if you click on this, it'll take you to a video of me solving the quiz and basically explaining the common mistake that a lot of people made. I'm not going to solve it today because I don't want to waste another 10 minutes on it when I already made a video, so if you watch the video and you still have questions, feel free to ask in the Google group or whatever. But that's there for you guys. Today I'm going to work some examples, discuss a couple more formulas, and then I'm going to do the live DC circuit demo. I brought some circuit stuff, so I'll build it under the camera. That might be, I think it'll be beneficial so that you guys can get a look at what a real resistor looks like, what a real circuit looks like, kind of less theoretical, and it'll be, applicable, especially when you take labs. The other thing I wanted to do before I even ask if there were other questions is homework, what was it, 1C? Is that the one everybody struggled with? Homework 1C. So this problem right here, I'm going to solve it by hand so you guys can see how I do it, and if there's any questions about how I do it, stop me. I have a feeling I know a lot of people where they got stuck, but let me just write it down real quick before I switch screens. Okay, 5 milliamps, 1K, 6K, 2K, 1K. All right. Great. All right, cool. So that's the circuit. The first thing everyone should notice is that the 1K and the 6K are in series, so I can combine those. And then the 1K and the 2K on this side are also in series, so I can combine those. So I'll get an equivalent circuit here, where this is 5 milliamps. And now I just have one resistor on either side. And that's going to be 7K because I add those in series, and then this is going to be 3K. This is still ground, obviously. So now I think this might be, is this where a lot of people got stuck? You didn't really know what to do next? Maybe people didn't get stuck. Basically, what it seemed like from what we were talking about in the Google group is people got stuck here. So what you do next is you can't really determine, you know this 5 milliamps because of KCL, it splits into two currents, and those currents will sum to 5 milliamps. Basically their sum will be 5 milliamps, but you have no way yet of solving how much current's flowing in either side. So what you need to do is you need to create another equivalent resistance with the 7K and the 3K, and notice that they're connected in parallel. If you remember what I said about parallel resistors, they share two nodes. And if you notice the 7K and the 3K, they share this ground node, and they also share this other node. So those two resistors are in parallel, and we can combine them. Okay, so if I wanted to combine those, I know I have to go product over sum, so 7K times 3K over 7K plus 3K. I think that is 2.1, if I remember correctly. It is? Yeah, 2.1. Alright, let's save some time. 2.1K. So now I have a final equivalent circuit. So I went from this circuit to this circuit, and now I'm going to go down to this last circuit here, where I just have a single resistor and a single current source. And basically this is 5 milliamps, and this is now, what did I say, 2.1K. Okay, so now I can solve this circuit. So let me use a different color. I know my 5 milliamps is flowing in this loop, right? Thus, I can find the voltage across this resistor, this equivalent resistor, which is basically all of the resistors now combined into one. I know this is 0 volts. If I use Ohm's law, my voltage across that resistor is 5 milliamps times 2.1K, which gives me 10.5 volts. And that's the voltage drop across this resistor. I know this is 0, so then I know that this voltage here is 10.5 volts. Any problems with that? Okay, so now the problem is you have to work backwards. So that node, which is basically, if I wanted to like number these nodes on this current source, and I called this node 2 of the current source, that's that same node all around. So that voltage, 10.5, is the voltage here, it's the voltage here, and it's the voltage here, because that node hasn't changed. So now what I can do, since I know that I have 10.5 volts on this node, is I can go back to this circuit, and I can find the current flowing through this 7K, and I can find the current flowing through this 3K, right? So if I take 10.5 volts, right, so I'm going across this resistor, 10.5 minus 0, because that's ground, divided by 7K, that gives me 1.5 milliamps. And on the other side, I do 10.5 volts minus 0 over 3K, and that gives me 3.5 milliamps. So now you see from KCL, right, those currents, this one, this 3.5, and this 1.5, those sum to this 5 milliamps. That's basically what we said when we did KCL, right? If I have a current going into a node, the currents out of that node are equal, the sum of those currents is equal to the current into that node. Okay? So now I know I have 3.5 milliamps flowing in this branch, and I have 1.5 in this branch. So now I can come back over to this circuit, because I have 1.5 flowing here, milli, and I have 3.5 milli flowing here. And now I can find V1 and V2 using those currents. So if I take this 3.5 milli times this 1K, then I get 3.5 volts here. And if I take this 1.5 times this 1, then I get 1.5 here. That good with everybody? Alright, cool. So were there any other problems with the homework before I move on to new stuff? Alright. So now, this stuff isn't super new, but I'm just basically doing something that we've done previously, but I'm going to make it simpler. Alright, so we're done with this page. Switch colors. So basically on homework 2, yeah, we saw some circuits that looked like this, right? We have a voltage source, and we have some series resistors, right? You guys remember seeing these circuits? Okay, this is a specific type of circuit, and it's called a voltage divider. You need to remember that. You're going to see them everywhere for the rest of your electrical engineering career. They're very important, and the reason they're very important is because basically it's a small system where this voltage here is we'll call it V in, and this voltage here is V out. And you can basically achieve whatever output voltage you want based on the ratio of the resistors. And I'm gonna solve that, basically derive that here, so that you can see what I'm talking about. But this is called a voltage divider, and I'm gonna go over this one first, and then we'll do some examples. This is basically what's on your homework for today. I switched the homework. I don't know if anyone looked ahead to homework 4, but I switched it. It's basically very similar to homework 2, except I'm telling you, do not combine the resistors to form an equivalent. Instead, you're going to use the voltage divider equation that I'm about to give you. And then down here, these type of circuits are called current dividers. And you're going to use the current divider equation. You're not going to combine these in parallel. So if you don't follow instructions and you solve them the same way you did on homework 2, then you're going to lose points. Okay? So back here. This is called a voltage divider. Let's call this R1, and we'll call this R2. And then this voltage source is just some voltage V. We don't know that voltage yet. All right? So if I wanted to solve, this is a derivation. So if you want to copy this, you can. You don't have to copy it. I'm just going to derive the equation for you guys. Okay? So I know that I have some current I flowing in this circuit, right? We don't know what that current is yet because we don't know anything about the circuit, but we do know that there's a current I that's flowing. That current, if I wanted to find it, I could find it by taking the two voltages on either side of R1 and dividing them by R1, right? Okay, so I could say that I is equal to V in minus V out and divided by R1. Everyone agrees with that? If I wanted to find the current, I could also do so by finding the voltage across R2 and dividing by R2 because it's the same current, right? So I could also say that I is equal to V out minus 0 divided by R2. Or in other words, just V out divided by R2, right? So now what I have is I have two equations that are both equal to I, okay? So I can set them equal to each other because they're both equal to the same current. So V in minus V out divided by R1 is equal to V out divided by R2, okay? Now what I'm going to do algebraically is I want to get all the V outs on one side so that I can solve for V out, because what I'm going to do is I'm going to provide an equation that gives me V out if I know V in, R1, and R2. Okay? And that's really useful because that means we don't even have to find the current. We can find V out without even knowing the current. It's just based on the ratio of the resistors and the input voltage. Okay, so algebraically I can split this into two fractions. V in over R1 minus V out over R1 is equal to V out over R2. And now I'm going to, like I said, try and get V out all together on the same side. So I'm going to add this term to both sides so that it cancels from this side. So then what I'm going to get is V in over R1. This term's gone. I added it to this side. So it's going to be V out over R1 plus V out over R2. Okay? Now I just need to solve for V out. I need to get V out all by itself because then that will say V out is equal to some equation in terms of V in and the resistors. So what I can do is I can pull, so I'm leaving the left side alone. I can pull V out of this equation, right? I can say V out is equal to 1 over R1 plus 1 over R2, right? And now I can divide both sides of this equation by this little piece right here, and I'll have V out all by itself, right? So if I divide by 1 over R1 plus 1 over R2 on both sides, it looks like it's getting crazy, but some stuff will cancel and it'll work out to be pretty nice. So this whole thing cancels. And what I'm left with is, let me go to a new piece of paper. See if I can kind of keep that. How's that? Nice. Alright, so I basically have V out is equal to V in over R1, and that whole thing divided by 1 over R1 plus 1 over R2. Okay, so this is still ugly. What I can do is I can multiply the top and the bottom both by R1 times R2 to get rid of these fractions. Because if I take R1 times R2 and I multiply it here, then the R1 cancels. So just looking at the denominator here, R1 times R2, so I'm basically distributing, right? R1 times R2 multiplied by this term gives me just R2, because the R1 and the R1 cancel. R1 times R2 multiplied by this term gives me just R1, because the R1 and the R2 cancel. Okay? And now, what I'm left with up here is the R1s cancel, but the R2 doesn't. So I basically have Vn times R2. Right? So this R1 cancels with this R1. And so now I can rewrite this a little bit neater by pulling the Vn out. And I can say V out is equal to Vn times R2 over R1 plus R2. So that right there is called the voltage divider equation. Is everything on the screen? Yeah, good. I can get rid of this now. So this is my voltage divider equation. We're going to use this a lot. You're definitely going to use it on the next homework. And all it's saying is if I have a circuit, right, that looks like this. This is my V in. Got some resistors here. R1, R2. And this is my V out. I can find V out by multiplying V in by this ratio of the resistors. Okay? So let's do an example. Let's look at one from last homework, from homework 2. Let's look at this problem C. So basically 12 volts, and then I've got 5K and 1K. Okay, this was called VSC, this was called VOC, right? So let's go back to the camera. And so basically, I don't need to, typically, right, what you guys knew before you came in here today is that you would combine the 5K and the 1K, you'd get a 6K resistor. You would go ahead and go 12 volts divided by 6K, you find the 2 milliamps, work backwards. It's kind of a pain. You don't need to do that anymore because we have this equation. So in this case, my V out is my VOC, right? So my VOC is equal to my V in, which is this voltage. What's that voltage? 12 volts. 12 volts. R2 over R1 plus R2, so 1K over 1K plus 5K. You notice 1K divided by 6K is just 1/6, right? So it's 12 over 6 gives me 2 volts. And that's it. That's this voltage right here. So let's go ahead and put it in Spice just so you know I'm not lying. I feel like I haven't done Spice in a while. Does anybody have any like serious issues with LT Spice? Like you still have problems using it, or it's frustrating to you because you don't know how to do something particular? Yeah.
Is there a shortcut for the current thing, the current flow device?
Yeah, so if you use the function keys, which is what I use, and you hit F2. Oh, you mean like a shortcut, like you don't have to do this?
Yeah, like you can press V to get a battery immediately.
I don't think so. There might be.
Yeah.
What did anybody see that group I sent, and it gave basically all of the LT Spice shortcuts? I sent it in the Google group, but I don't know if anyone saw it.
I saw it.
Maybe it was in drafting. Hotkeys, yeah. So this is everything right here.
Oh, okay.
Place inductor, capacitor, ground, component. I don't see anything that says current source.
Oh, okay.
You may be able to change these if you want to make a shortcut. It doesn't. Yeah, they look like you can change them. So if you wanted to make one, you could. But I don't think there's by default there isn't any. All right. So what do we have? We had a 5K and a 1K. This was 12 volts. This is ground. And then this is V out, C, VSC, and I dot OP. And I run it, and I get 2 volts. So this is exactly the same problem you had on homework 2, and you had to find it using the series resistance equivalent. You don't have to do that anymore because you now have the voltage divider equation. Anybody have any questions about anything I did as far as this? Yeah.
What is .op?
Operating point. So
Why
it's
do
a.
we need that?
Why do you need it?
Yeah.
So it's basically in Spice. You don't. So I hit S, right, and I just type .op because I know the commands. But say I didn't have anything in here, and I try to run this. It's going to ask me what kind of operation do I want to run. Basically, I can run all these different things. So DC operating point is the one that I'm running because we're just trying to find voltages and currents. All these other simulations are used for different things. We'll use a couple of them later in the class. We'll use DC sweep. We might use AC analysis. We'll definitely use transient. But as of right now, operating point is the only one that we need, so I just type .op. But if you just hit .op, right, it'll basically type .op for you. I don't even have to type it, but I just do it because it's quicker. Any other questions about any of the math or anything that I did here? Yeah.
I wanted to see, how do we know which one is going to be R1 and R2?
So it doesn't matter which one's R1 and R2 by name. What matters is which one's connected to the source and which one's connected to ground. So the one that's connected to ground is R2. The one that's connected to the source is R1. So when you look at this equation, this resistor is always going to be the one that's connected to ground. And this resistor, R1, is always going to be the one that's connected to the source. So their names might not be R1 and R2, but just know that like if I had this circuit and I called this RI, I guess, and then RF or something, like initial, final, I don't know, the equation would read, and then this is, let's call it V2 and V1. It would be V2, that voltage that I'm trying to find, is equal to V1 times RF over RI plus RF. All right. I saw another hand, yeah.
So if it's in a case where there is more than just 2 resistors, do we still have to combine them to make them into just, okay.
Yeah, so I'll do another quick example because I was going to cover that too. So say you have a circuit that looks, I don't know, I'll do just something random. Let's say we've got voltage source, resistor, and then maybe 2 resistors like this, right? And then this is ground. Say, I don't know, 8 volts, 2K, 4K, and 6K. Okay? Now, what I have to do first is I have to find this equivalent resistor so that I can get it in the form of a voltage divider, right? This isn't quite in the form of a voltage divider yet. It's good if you can recognize it as a voltage divider, but you have to get it in that form before you can use the equation. So I basically have to say REQ is equal to 4K times 6K over 4K plus 6K, and I think that's 2.4. Okay, is that right? So then I would redraw the circuit, of course. You don't, and again, you don't have to redraw the circuit. Once you guys get good enough at this stuff, you're not going to want to redraw the circuit. You're just going to be like, oh, I can just plug 2K and 2.4K into my calculator. But for the time being, we know this V in, we don't know V out. We want to know V out. We go V out is equal to 8 volts, which is my input, right? Multiplied by 2.4K over 2K plus 2.4K, and then whatever that number is you're out. That's your V out. That makes sense? Is that what you're asking?
Yeah.
Yeah, basically, you can't use the formula unless you get it in this form. So if you see a circuit that you're like, oh, I could combine those in parallel, I can combine those in series, and then you get to this form, then you can use the equation to find that voltage. Yeah.
So that was for resistors, but all three of them were in series. You just have to combine two of them.
Exactly. So you could combine either of the two. The problem is, if you did so say you had a circuit like that, you just have to keep track of which nodes are which. So say you had something that looked like this. So those are all in series, right? So if you wanted to find this voltage, it would make sense to combine those two. If you wanted to find this voltage, it would make sense to combine those two, right? So just make sure you keep track of which node you're trying to find the voltage for. And if you want to find all of them, you're better off. In that case, you might be better off to just combine them all in series, find the current, and then find the drops across all of them. Like I said, guys, there's a lot of different ways you can solve these. I'm just going to present you with all of them, and then by the time the midterm and the final roll around, you're basically going to take your pick at which. I'm going to ask you solve this one using this, solve this one using this, but there will be several circuits on the midterm and the final where I don't tell you how to solve it, and you're just going to be like, oh, I know that, I can use this method. Okay. So if you, yeah.
Can you use KVL on that to get the voltages on each one?
Yeah, you could. You can't use KVL unless you have one loop, because the equation. So once you get it in this form, you can use KVL. So if we wanted to use KVL, we'd write a little loop equation, right? So I'm going up by 8 volts there, so I'd say 8 volts. I'm going to drop across this resistor, so I'd write minus I times 2K, and then I'm going to drop across that resistor, so I'm going to write minus I times 2.4K, and I set that whole thing equal to 0, solve for I. But in this form you can't, because there's 2 loops technically. There's a current flowing in this loop, and then there's a current flowing in this loop. The reason KVL works is because the current is the same in the entire loop. So once you have one loop, you can use KVL. Any other questions? All right, I'm going to move on to the current divider now. This was the voltage divider. Let me label it again. All right, current divider. Switch colors. All right, so when I started the voltage divider, I gave us like a theoretical circuit that was like a voltage source and 2 resistors in series, because that's the standard form for the voltage divider. The standard form for the current divider, so let me write it, current divider is a current source with 2 resistors in parallel. So we've seen all this before, nothing new, it's just going to be a new equation. All right. So I basically have my current I, I'll call it IT because I like to call it I total basically, because I know that this is going to branch off into 2 different currents. This is going to be I1, this is going to be I2. So what the voltage divider does is it divides down that source voltage. Whatever my source voltage was, it divides it down. You'll notice that in these circuits, you're never going to have I think I might have mentioned this last time, you're never going to have a voltage somewhere in the circuit that's greater than the source voltage, because basically the source voltage is providing all the energy for the circuit. So you're not going to have an 8-volt source and then somewhere else in the circuit have a 10-volt voltage, because that's not, basically when current's flowing through a resistor, voltage gets lost. And so it can't ever surpass whatever that input voltage source is. It's the same thing with current. So if this current is 10 milliamps, these 2 currents have to be less than 10 milliamps because that 10 milliamps got distributed between the 2 branches. So the voltage divider divides the voltage down, the current divider divides the current down, and it just uses an equation, so you don't have to combine the resistors in parallel, but I'm going to derive it. So we'll call this voltage V. We don't know what that voltage is. We don't know any of the currents. However, I got to call this R1, and I'll call this R2. We do know that I1 is equal to V, I guess minus 0 over R1, right? But I'm just going to say V because I'm going to exclude the 0. Everyone knows it's the voltage across the resistor, right? It's V minus 0. Okay, I2 is equal to V over R2. Okay? And then I total is equal to V over the equivalent resistance, right? It's basically equal to the V over whatever that equivalent resistance is. I think I did this in class the day that the lecture didn't have audio. Basically, when I say IT is equal to I1 plus I2, and I plug all those equations in, I get V over REQ equals V over R1 plus V over R2, right? Because it's these two currents sum, and their sum is equal to this total current. If I cancel all the V's out, basically I can cancel V from all three of these. I get that 1 over REQ equals 1 over R1 plus 1 over R2, and that's where my equivalent resistor formula gets derived from. Oh, I don't want to rederive it, so I'm just going to write it. We know REQ is R1 times R2 divided by R1 plus R2, right? That's the product over sum formula. Okay, so I know that my I total is V over R equivalent, and that this right here is R equivalent. Okay, so let me go ahead and plug this entire equation in to this. V over basically this whole thing. And basically dividing by this whole thing is the same thing as multiplying by its reciprocal, right? So I can say that IT is equal to V times R1 plus R2 over R1 times R2, right? That's the same thing. Okay. So now, let's say I wanted to solve for I1 or I2, because I'm trying to find, basically in the voltage divider I was trying to find that voltage between the two resistors. This time I'm trying to find the current through either one of the resistors. So I can say that V is equal to IT multiplied by this big giant thing, by the product over sum. And then I can take this V and I can plug it in for one of these equations. So I1 is equal to V over R1, but let me write V in terms of my total current and my resistors, so then I don't need to know any of the voltages. I only need to know currents, right? That was the point. It's basically to eliminate a variable. So if I plug this V in right here for this V, I can say that IT times R1 times R2 over R1 plus R2, and then I had that whole thing. That's my V basically divided by R1. So these R1s cancel. And I get that I1 is equal to IT times... Oh, you know what? Hold on. I made a mistake. Can somebody spot my mistake?
James, in there, the second IT
Should be only the
into R1 into R2, you cancel out the R1. I don't know if you can see.
Oh, I canceled the wrong R1.
Yeah.
It's this R1.
Addition.
It's that R1 that cancels. Okay, that's what I did wrong.
It's not canceled, the addition.
Yeah, this doesn't cancel. It's this R1 that cancels. Yeah, sorry guys. Let me do that over again. I'm not gonna make you guys sit through the whole derivation again. But let me just fix my mistake. So basically I had gotten it to the point where my apologies. Alright, so I had gotten it to the point where I said that V was equal to basically I total multiplied by my equivalent resistance, right? And my equivalent is R2 times R1 divided by R2 plus R1. We know that I1 is equal to V over R1, and we know that I2 is equal to V over R2, right? So now if I plug this V into one of these equations, I get I1 is equal to V, which is this whole thing, IT times R1 times R2 over R1 plus R2, and divide by R1. This cancels with this, and I get I1 is equal to my total multiplied by R2 over R1 plus R2, right? That's my current divider equation. So it's very similar to the voltage divider equation, right? It looks almost identical, except we're swapping the voltages for the currents. And so if I wanted to find I2 instead of I1, I would basically do the same thing, except the R2s will cancel. So I get that my I2 is equal to this equation. So what you note here is that if I wanted to find the current that's flowing through R2, I need to take the ratio of R1 over the total resistance. And see, the thing to note is that you're still adding these two resistors. You're not combining them in parallel right here. You're adding them. So make sure you don't overanalyze and think that this is some parallel thing going on. It's definitely the sum of the two resistors. Okay? So, but the thing to note is that if I want to find the current flowing through R2, I'm looking at R1 over the sum of the resistors. If I want to find I1, I'm looking at R2 over the sum of the resistors. So let's go ahead and do another, like a quick example from the last homework again. Let's do the first one, because that's the simplest one. Let me switch colors. So I've got 4K, 5K, 1 milliamp. So basically I want to find, in this case, say I asked you to find the current through the two resistors and I wanted you to find this voltage V. So you know that you can find I1, this current, and you can find I2, this current, by just using these formulas. Okay, so my I total in this case is 1 milliamp. So if I wanted to find I1, I would say I1 is equal to 1 milliamp times, in parentheses, R2, right, which is 5K, over R1 plus R2, which is 9K. So is that like 0.555 milliamps, something like that? And that's like, it's going to repeat. So that's my I1. And then if I wanted to find I2, I could do one of two things, right? I could either use KCL now. I can say 1 milliamp minus that 0.555 gives me the rest of the current, which would be 0.444 or whatever. Or you can use the other equation, which is going to be I2 equals 1 milliamp times 4K over 9K, which will give me 0.444 milliamps. Any questions? Yes?
So it's essentially just using the resistor that you're looking for, and then dividing it by the equation of both the resistors?
Yeah, so basically if you're looking for the current through, this is the thing that you have to keep in mind. When you're looking for the current through this resistor, right, so that's I1. That current I1, it uses the other resistor in the equation, because this resistor got canceled out. And when you're looking for I2, you're using this resistor in that equation. So it's basically whatever resistor you're trying to find the current through, the other resistor goes in the numerator. So just make sure you keep that in mind. If I'm trying to find I1, I use basically R2. If I'm trying to find I2, I use R1.
So then if you had 3, would you just add the other 2 together on top?
So if you had 3, this would have to be re-derived, because the equations wouldn't work out the same. What you would do if you had 3 is similar to Dara. Is it Dara or Dara?
There.
Dara's question. Basically, you'd have something like this, right? And you would go ahead and combine 2 of them in parallel, and then you're back to this form, right? So you can take 2 of them, combine them in parallel, and then you'd end up with something that looks like that, and then you can solve it. And again, like I said in the voltage one, you got to be conscious of what voltage node you're looking for. In this case, say I wanted to find the current that's flowing through this resistor, and I have 3 resistors here. If I combine these 2, and then I find the current flowing through that equivalent, now I know that my I total minus that is this current. So just keep in mind which current you're trying to find when you decide what resistors to combine in parallel. Basically, when I went over that homework problem today, I was getting at the fact that, you know, we had those two resistors on either side of the current source, and we combined them in parallel. And some people came to my office and said, like, I didn't know you could combine those in parallel, because they thought that they had to be right next to each other. So now, is everyone comfortable if I said, like, if I combine these two outer resistors, they're still both sharing two nodes, so I can combine those two outer resistors in parallel, and that's fine. You guys understand? As long as they're sharing two nodes, they're in parallel, and you can combine them. All right, any other questions about current dividers or voltage dividers? Yeah.
What are their uses?
Their uses?
Yeah.
Well, basically, a lot of times in a particular circuit, you might need. So I'll give an application that's not necessarily relevant to you guys now, but it will be in the future. So say there's these devices called MOSFETs. I'm sure you guys have heard of transistors.
Yeah.
So a MOSFET is a certain type of transistor, and they need a certain voltage at their gate. So I'm going to draw a MOSFET. Don't worry about this. You guys aren't going to be tested on this. This is just an application. So this is what a MOSFET looks like. Basically has three legs: the gate, the drain, and the source. And what it does is it either allows current to flow through from the drain to the source, or it doesn't allow current to flow through the drain and the source, depending on the voltage that's at the gate. Okay? It's like an electronic switch. It'll either allow current to pass through, or it won't allow current to pass through based on this voltage. So say I have a 9-volt battery, right? And the MOSFET only needs 5 volts at the gate in order for me to allow current through. I would use a voltage divider, and I would take that output, so this would be my voltage divider, and let's say I just want it to have 5 volts there, right? So if I wanted to have 5 volts there, I could put 5K here, I could put 4K here. That if you combine those, right, I get 9K, that's 1 milliamp, so 1 milliamp across this 5K would give me 5 volts. And now I would connect that to my MOSFET. So that's one application. That's just one practical application. And there's also other times where you might need a certain amount of current through something. That's where the current dividers are used. More or less, these are small subsections of real circuits, right? Most circuits in the real world are not this simple. But these circuits will show up as like subsections of larger circuits, and you go, oh, okay, I know the voltage there because that's just a voltage divider. And all throughout this class, we're going to do things where you're going to see these circuits, and likely you're not going to see a circuit like that in the real world, because circuits in the real world are much more complicated. But you will see subsets of the circuit that use circuitry that we're going to cover, and then you'll know, oh, the voltage there is this, the current there is this, and it'll give you an idea of how to break it down. To really analyze real circuits, you're going to have to get through EE220, 221, 320, because that covers all of the components that you might see in a real circuit. Any other questions?
Is there a lab component in 221?
Yes. Yeah, there is a lab component to 221. So, actually, yeah, now that we're done with, if no one has any other voltage and current divider questions, I'm going to go into the breadboard, and I'm going to start showing you guys what you will see in the 221 lab, and I think it'll be interesting. Yeah.
I have a random question. Is there going to be a 221 for summer?
A 221 for the summer?
Yeah.
I'm not sure. I have no idea. I can find out and let you guys know, but I'm not sure.
I'll tell you. I think we also got an email that showed all the summer classes as well. It was a couple hours ago, actually.
Oh, all right. Well, yeah, there you go. I'm not sure. All right, so if there's no more questions, I'm going to go into the little demo that I had planned. I got about 15 minutes, and then I'll give you guys the quiz. But, yeah. All right, let's go. So let's see how this looks on camera. This is clear. Nice. Alright, so I built a little breadboard circuit. I'm going to put it together. Let's see how clear it is under the camera. That's kind of blurry. That's probably fine, right? All right, so basically up to this point we've been talking about voltage sources and resistors, right? We haven't really, and current sources, but like I said, current sources aren't really a thing. They're out there, but we don't see them very frequently. They're used for testing more than anything. All right, this is a 9-volt battery. It's got, a red and a black wire. The red and the black are the positive and the negative terminal of the battery. So in SPICE, all I would have with my battery would be something that looks like this. 9 volts. And that's it. I haven't connected anything anywhere yet. So I could call this, V red, and this V black.
Real quick with Spice, do you know how to get that to flip down?
I don't.
I did it on accident the other day, and I don't remember what I did.
If you put it on the corner, it'll flip it down, but I don't know if you do it anywhere else if it will. So if you put it on the corner, it'll put it in the bottom, but otherwise I can't figure out. If you figure it out, please let me know, because I've been wondering too. Alright, so this is basically what we've got so far. We've got a battery. It's got a red and a black. I soldered some legs to it so that I can plug it into my breadboard. How many of you guys have used a breadboard before? Okay, so most of you guys know how they work. For those of you who don't know how they work, I sent myself a little link. Basically, it's a board that you can plug components into, and it has conductors built into it, so you don't have to use a boatload of wires. You end up still having to use a boatload of wires, but much less than you would if you didn't have the breadboard. I know I sent it to myself. Let's see. TA meeting. You know what? I'm just going to Google it again. I think it was SparkFun. So basically, the breadboard has. So this is why it's called a breadboard. They used to build circuits on breadboards before these breadboards were invented. It's because wood is not a conductor, so they can put stuff on the board and it's not going to move around. I guess it's sturdy. But what we have are these breadboards, and inside the breadboard, there's basically horizontal strips of conductor. So when you look at the breadboard that I have here, these holes that are going across, right? You guys can see my cursor? The holes that are going across, those are connected. That's just a wire. So, these are numbered, right? 1, 2, 3, 4, all the way down to 30. So row 1 is not connected to row 2, but this hole on row 1 is connected to this hole on row 1, right? 1A and 1E are connected. That's what we see here. That's just a piece of metal. It's just a conductor. It has virtually no resistance. There is some resistance, but it's basically just a wire. And so if I come over here and I want to build a little circuit, I don't know if you'll see it, but I'm going to plug in my battery. Right now I have an LED connected, and basically it should light up when I plug this into the breadboard, indicating that I have power. Oh yeah, you can see it. So I typically connect LEDs to my breadboards just so that I can know when there's power there and when there's not. That's not necessary for what we're doing. I'm just going to build a voltage divider, and I'm going to measure the voltages so you can see what a real voltage divider is, and then we'll go do it in SPICE so we can see that it's the same. So I imagine those of you who know what a breadboard is also know what a multimeter is. I brought a multimeter. If you don't know what a multimeter is, it's basically a piece of equipment you're going to get familiar with over the next couple years. It has a lot of different features. It can measure voltage AC, voltage DC. It can measure millivolts, ohms, capacitance, resistance, current. It can basically measure any number of things that you might need to measure in an electrical circuit. So first, I'm going to go ahead and measure the voltage of the battery so that we can check what my actual potential is. So I'm measuring the voltage between my red and my black. I'm going to use these two connectors, and I'll get a voltage reading. Nobody can see that. Can you guys see that? Okay? Yeah. Good enough. Oh, let me shut this light. Maybe it'll be better. There we go. All right, so I'm going to probe the red. And right now, see, I'm not getting any reading, because when you want to measure voltage, you need to measure the voltage across something. You're not measuring voltage at a point, you're measuring the voltage across something. So I'm going to measure the voltage across the battery, and that voltage should be somewhere around 9 volts. So yeah, 9.57. So just to be accurate, let's go over to Spice and make this a 9.57 volt voltage source. Alright, so that's my battery voltage. Now I've covered the breadboard, I've covered the battery. I have resistors here too. So this is what a resistor looks like. I have it in my left hand. I'll Google some too so we can get a better look at it. Through hole resistor. Alright, so these are resistors. Resistors have a color code on them, and that color code tells you basically, I think it's the first digit, and then the multiplier, and then the tolerance. It's kind of a pain. Some people have it memorized. I certainly don't. But you can look up resistor color code calculators, and then you can just plug in the little numbers and get the value out for whatever that resistor is. But that's a nightmare too. I don't like that either. So what's good about having a multimeter is that it has an ohm setting, and we can just measure the resistance. So if you take one prong on one side of the resistor, you see how I'm probing it, and then one prong on the other side, I'm going to measure the resistance here. You see it's 2.165 kilo ohms. You see the K? So that's 2.165 K. So let's call that my R1. 2.165 K. Alright, so that's what I've got so far. I haven't connected it yet, so let's kind of delete that. I want to do this in order. Alright, so I've got my battery, I've got one of my resistors. Let's measure the other resistor. I grabbed two like resistors so that I could make a voltage divider that splits the voltage in half, basically. And this one's 2.160. Alright, so let's go back over here and make another resistor. 2.160. Okay. Alright, so I've got my resistors, I got my voltage source, so now what I'm going to do is I'm going to go to the breadboard, and I'm going to connect them, and then we'll do some measurements. Alright, so first, basically, I have power rails on my breadboard. You see the plus and the minus? That's why I soldered these as such, so that the red of the voltage source would go into the plus, and the minus would be the black, right? So when I plug that in, this entire rail now, the blue side has 0 volts, and the red side has 9 volts, okay? Or 9.6, whatever I measured. So first I'm going to put a little wire to branch off of this is called a bus. Basically any like long wire that you can tap off of is called a bus. So I'm going to tap off of the bus, and like I said, this entire row is conductive, so I can connect my resistor anywhere in that row, and it's going to be connected to my red. So basically what I just did, if I was going to do this in Spice, is I just connected the red of my battery to the first leg of one of the resistors, right? So this is exactly what I just did. I still don't have this resistor connected. Okay. And now I'm going to connect my other resistor. So this one is in row 8. So I just have to connect the other leg of my resistor somewhere in row 8. And now these two resistors are connected through the breadboard. Here, let me do this. It might make it easier to look at. And now I need to ground. I basically need to connect my bottom of my other resistor back to ground. So what I just did was I connected this resistor. Wow. I connected this resistor like that. Let me rotate this so I don't know. And now I need to connect this down to the black of the battery. So I use black wires to note ground, and I use red wires to note power. It's a good practice to get into. So there's that. And that's just basically bridging that gap, and now I'm going to connect this to the ground of the battery, and now I have my voltage divider completed. And so basically what I just did is this. And so in general, the black terminal of a battery should be connected to ground, so we're going to ground it. and that's my circuit. And that's exactly what I have here. So now what I'll do is I'll go ahead and run this in Spice, and we'll get some voltages, and then I will also get the currents, and I'll show you guys how I measure voltage and current with the multimeter. So let's run. Here, let's call this V out, because this is my voltage divider.
Where is the ground on the breadboard? Is it like a specific component, or is it just back to the negative terminal?
It's just back to the negative terminal. So when you connect, basically the battery has 9 volts across it, but in general, ground is not a physical thing. It's just a node. And so we call the black terminal of the battery, or the minus terminal of the battery, ground.
Okay. How does the third prong work for our outputs then?
So those are connected to the ground of the building.
Okay.
So whatever building you're in, that third prong is connected to the building ground, and it's just a large node. It's like a return path for all the current.
Okay.
Yes.
Is, when we talk about ground, is that interchangeable with referring to like the neutral when you're talking about actual wiring? Because I did an interior wiring, so it's throwing me off when you say ground, because in this instance, I would call that neutral, so I'm back to the neutral bus.
So I guess with AC, right, you have hot, neutral, and ground.
Yeah.
So AC and DC are different.
Right.
I don't know a whole lot about wiring, if not anything actually. I just know that those three are called what they're called.
Okay.
But I know that in AC you need a return path, and in industrial wiring you need a return path, and ground is basically acting like our return path.
I guess I just used the AC, that's why I'm thinking that.
Yeah. So ground and return path are kind of interchangeable in DC. I think in AC they're different.
Yeah.
So, yeah.
Don't you have to put a load on it? What's the load? Is it LED, right?
So I don't have that LED connected to the voltage divider. I just wanted to show that I'm proving that my breadboard's powered up with the LED. So here's the thing with a voltage divider. If I were to connect any load out here that draws any current, it would ruin the voltage. So that's why earlier when I showed that application, I showed a MOSFET, because MOSFETs don't take any current at the gate. So that could be an actual application where you would use a voltage divider to drive something. But if you connected anything out here that pulls any current, it's going to ruin it. So back to this. Did I run the .op? No. Let me run it. So my 4.779 volts is what I got out. So let's see what I get out of my. Basically, when I'm measuring the voltage at a node, I say the V at V out. What is that? That's the voltage with reference to ground. So that node is 4.779 volts greater than ground, right? So I'm going to measure my voltage using the multimeter with my plus terminal connected to the output of the circuit, and I'm going to connect my minus terminal to ground because ground is my reference. So what I'm going to do is go back to the camera. 4.779. It's not going to be exact, but it'll probably be close. It might be exact. Nice. Plus. Oh, thanks. It would have measured the resistance again. But, alright, so what do we say? 4.779. So let's probe this, and then we'll probe ground. So it's 4.8, basically the same, right? And so we know that, right, if I go back to Spice, we know that I had 9.57 at the red, and we have 4.779 at the V out. So if I subtract 9.57 minus 4.779, that's telling me I should have 4.79. So I just subtracted those. Basically, oh wow, you guys can't see that. Alright, well, believe me, it says 4.79 should be across the other resistor, so now I'll measure the voltage across the other resistor too.
So are those leads
4.79.
just little hooks on the end?
That's right, yeah, so I have a little, like, push. You see how I push it in? And it pops a little hook out, and then it closes.
Cool.
Yeah, so these are called quick connects. So one last thing I want to do, and then we'll do the quiz, is I want to show you guys how to measure the current. So the voltage in a circuit you can measure by probing across a component, and it'll tell you the voltage on one side, the voltage on the other side. It subtracts those, and it outputs that difference. With current, you cannot just connect the multimeter to the circuit. You have to connect it in series with whatever wire you're trying to find the current through. People do this all the time. They'll go and do exactly what I just did. They probe both sides of a resistor to find current, and what that does is it provides a short circuit through basically around that resistor. Because what you do with the multimeter is when you connect it in series, the multimeter is offering basically no resistance, and it's letting the current flow through it and reading what that current is. People will like try and measure the current through an LED, for example, and they'll go ahead and like probe both sides of the LED, and now you have a short through the circuit, and you'll get this huge current. I was just helping some guys the other day. They basically tried to find the current through the circuit by doing the wrong, like by probing across a resistor, and they popped one of their PCBs. Like the circuit board trace just flew out of the board. It burnt because of how much current was flowing, because they bypassed the resistance. You don't want to do that. What you want to do is you want to break the circuit. So first, when I say break the circuit, I don't literally mean break it. I mean you open the circuit so that it's not connected anymore. So now I had it connected in 8, right? And now I have it connected in 9. So this resistor is not connected to this resistor anymore because they're separated by one column or whatever. And now I'm going to connect my multimeter. If you have it in voltage mode and you have the probes connected for currents, then it starts beeping at you. So now I'm going to connect my multimeter between the two resistors where I broke the circuit. And what that's going to do is it's going to offer a path for current to flow through the multimeter. So now current's flowing into this resistor, and then it's flowing through this red wire into my multimeter, back out of my multimeter, and then into the rest of the circuit. So my multimeter is literally connected in series with those two resistors, but it's offering no resistance, so it doesn't change anything. So I don't think you guys can see that, but it's reading 2.2 milliamps. So let's see what LT Spice was reading. Basically 2.2 milliamps, right? So yeah, that's a little demo of circuits. I don't want to take too much time away from you guys' quiz, so I'm going to give them to you now. If you have any questions about anything, feel free to ask. And yeah, let's take the quiz. Where stop?